In the last video, I told you something that sounds impossible. A 1-inch pipe is not 1 inch. Today I'll show you why and how engineers actually measure, size and connect every pipe in a plant. Outer diameter, wall thickness, schedules, bore, the ends that hold it all together. By the end, you'll read a pipe spec like a pro. Here's the first thing to understand. Measuring a pipe takes more than a tape measure. A pipe's dimensions are defined by its size and its schedule. The standards come from ASME, specifically B36.10 and B36.19. And a full description always comes down to three things: the outer diameter, the wall thickness, and the length. Nominal pipe size, a number that is not a true measurement. From 1/8 of an inch up to 12 inches, the NPS does not match the real outer diameter. A 12-inch pipe, its actual outside diameter is 12.75 inches. Why? Because NPS was originally built around a consistent inside diameter, not the outside. And here's the rule that fixes everything. At 14 inches and above, NPS finally equals the true outer diameter. Outside North America, you'll see DN, nominal diameter. The same idea measured in millimeters. The outer diameter, the OD, is the real external measurement. And for a given size, it never changes, no matter how thick the wall. The wall thickness is set by the schedule. Higher schedule, thicker wall, smaller bore inside, and more pressure it can hold. Schedule 40 and Schedule 80 are the everyday workhorses. One detail the field never forgets. Mills are allowed a 12.5% tolerance on that wall thickness. So the spec is a target, not a guarantee. Pipes also split into two families by bore. Small bore, 2 inches and under, drains, vents, instrument and sampling lines. Often called non-critical, but don't relax. Small lines vibrate, and vibration means fatigue failure if they are not supported. Large bore is everything above 2 inches. And pipes don't come in one length. Single random length runs about 18 to 25 feet. Double random length runs 38 to 40 feet. Knowing which you're getting changes how you plan every weld on site. Now the part that decides how it all connects. The pipe ends. Plain ends, cut at 90 degrees. Simple for smaller sizes, joined by couplings or slip-on flanges. But they can trap liquid, so avoid them where erosion or crevice corrosion is a risk. Beveled ends, the weld end, cut at a 37.5 degree angle for a strong, leak-proof butt weld. The go-to for large diameter pipe. Threaded ends, threads cut into the wall, no welding needed. Perfect where a flame is a hazard. But threads cut into the wall, thin it and weaken it. Low pressure only, never for poisonous or flammable fluids. Grooved ends. A machine groove holds a gasket, a housing clamps it tight. Fast to assemble, easy to take apart. Socket and spigot. The bell joint you'll see in ductile iron and PVC. Tolerant of up to 10 degrees of misalignment, but low pressure only. Flanged ends. Bolted connections for when welding isn't an option and you need to dismantle later. The trade-off? They can leak and they dislike high bending loads. And buttress ends, bolted backing flanges, used in glass piping, low pressure only. So that's how a pipe is truly measured. Size, schedule, bore, and the end that connects it. Every one of those numbers is chosen on purpose for safe, reliable flow. Want to skip the lookup tables? Head to AIEnginear.com. Our free calculators give you OD, wall thickness, and schedules in seconds. If this cleared things up, subscribe and I'll see you in the next one.